Warning: the experiments performed in these lectures can be dangerous. Any attempt to perform these experiments on your own is undertaken at your own risk. Your lecturer is Dr. Richard Wolfson. Dr. Wolfson is the Benjamin F. Whistler Professor of Physics at Middlebury College. He holds a master's degree in environmental studies from the University of Michigan and a doctorate in physics from Dartmouth. Dr. Wolfson's books include Nuclear Choices, A Citizen's Guide to Nuclear Technology, and Simply Einstein, Relativity Demystified, both of which exemplify his interest in making science accessible to non-scientists. He also has published in Scientific American and writes for the World Book Encyclopedia. Dr. Wolfson's knowledge of electronics stems from his professional activities as a physicist and his lifelong interest in electronics as a hobbyist.
Welcome to Modern Electronics, a course in which I'm going to try to get you to understand the electronic devices that are so much a part of your world, that are around you everywhere. Why should you want to understand modern electronics? Well, the most obvious reason is that electronics are ubiquitous these days. If you're a member of our modern technological society, and virtually everybody is, and you certainly are if you're watching this course because you're using electronics to do that, then electronics is everywhere. Look at some of the things that you use that are electronic. Your iPad, your smartphone, your laptop, your TV, the instrument panel of your car, your GPS system, your camera, your loudspeaker in your audio system, the microphone that allowed us to record the music, and so on and so on and so on. In fact, the distinction kind of blurs because even your refrigerator or your toaster may have electronics in it. This lecture today is going to distinguish electricity from electronics. Two different things, electricity being a little more mundane, electronics being a little more sophisticated. I'm going to try to give you that distinction. And then I'm going to give you a little bit of background on basic electricity, not nearly at the deep level I would do in a physics course, but enough to get you equipped to handle what we're doing in here. So let's look at some definitions. If you take a formal definition of electronics, this one from Wikipedia, electronics is the branch of physics, engineering, and technology dealing with electric circuits that involve active electrical components, and I'm going to emphasize that one, such as vacuum tubes, transistors, diodes, and integrated circuits, and associated passive interconnection technology, which means wires and plugs and other things that connect these. Well, that's a great definition, but I like a simpler definition. My definition, which is not quite accurate, but I think is simpler and captures the spirit, electronics involves the control of one electrical circuit by another, and it involves using devices that allow that kind of control. Now, some would quibble. They'd argue there are electromechanical devices, things called relays, for example, that allow one circuit to control another, and we probably wouldn't call those electronic. But the essence of electronics is we have devices that allow one circuit to control another. Often it's a situation where a weaker circuit with weaker electrical quantities controls stronger electrical quantities. That's what happens, for example, in an amplifier. What's an electrical circuit? Well, an electrical circuit is some kind of interconnection of things called components, and I'll describe a number of electronic components as we go on, and it's intended to do something useful. It could amplify, it could display video, as in a television or a video monitor or a screen on your computer or on your smartphone. It could make sound, it could do whatever. And it usually, but not always, includes a source of energy. And I'll give you just a couple of examples of when it doesn't include a source of energy. I drove down to the teaching company studio, the Great Courses studio, yesterday with a carload of electronic equipment, and I went zipping through a number of toll booths, and I did so thanks to my EasyPass, which is basically an RFID device in which the source of energy came from outside. It was beamed at me by the toll booth, energized my circuit sent a signal back to it. So the circuit does not have to include a source of energy, but usually it does. So our definition of electronics is basically looking at how one device or one circuit controls another circuit, and we're going to look at the devices that do that. And I'd like to begin by giving you a simple history of electronic devices. This is about modern electronics, and if you look at the set behind me, you see many eras of electronic devices from fairly old to fairly modern. And I want to distinguish what's different about modern electronics. And surprisingly, to me at least, this always surprises me, there's less of a distinction than you might think. I've been teaching electronics for 30 years, and I teach basically the same fundamental ideas. What's changed is the devices we use, and more importantly, what's changed is the number of those devices we can cram into a given circuit. So let's take a look at a quick history of electronics. So I want to begin by talking about the devices that use one circuit to control another, because they've undergone a remarkable evolution since the early years of the 20th century, and yet their function is still the same. So let me begin. Some of you old-timers may remember vacuum tubes. Vacuum tubes were evacuated glass tubes containing metal electrodes, and electrons flowed in the empty space between these electrodes. The tubes were designed in different ways for different functions, but the basic function was there was an electrode in there. It was called the grid, and by applying different electrical signals to that grid, you could control the amount of current, the amount of electric current, which I'll introduce soon, that flowed through the vacuum tube. And this vacuum tube is probably from about the 1920s. It's a big, clunky thing. They're obviously very fragile with that glass envelope. They consume a lot of power because they have a hot filament, like a light bulb filament, that has to be heated and glow to give off electrons. But there they are, and that's what we had for most of the 20th century. Vacuum tubes got smaller as the 20th century evolved. There's one from probably the 1940s or 1950s. They got smaller still. Here's a miniature tube from the 1960s, probably, little tiny thing. Still has a whole lot of pins coming out the bottom to connect all kinds of things to it. And then a revolution occurred in electronics in the middle of in the 20th century, in about the 1950s to 1960s, came the invention of what is probably one of the most important devices ever invented in the 20th century, and that's the transistor. And the transistor did exactly what these vacuum tubes did. That it allowed one electronic circuit to control another, but it was much smaller, and more importantly, it was a solid-state device, meaning it was built out of solid materials, not a glass envelope with vacuum in it and electrodes stuck in there for electrons to flow back and forth. And so here is a transistor, a typical transistor. This is a modern transistor. The early transistors looked a lot like this. It has only 3 wires, which is the minimum number of wires it could have for one circuit to control another. This particular transistor probably costs less than $1 and can do the same functions as this large vacuum tube. So we obviously had an enormous miniaturization of electronics with the invention of the transistor. And in the 1960s and 1970s, everything was listed, oh, this is solid state. Solid state means it no longer had vacuum tubes, it had transistors. Here's a power transistor. It's built on a metal case that bolts down to a heat sink because it gets very hot. This could be used as the output amplifier of a stereo amplifier. It might be able to tolerate 100 watts of power or something like that. And then in the late 1960s and early 1970s came yet another development, which was the technological ability to put lots of transistors and other electronic components interconnected on a single tiny wafer of the element silicon. That was the integrated circuit. And integrated circuits contain anywhere from a handful to billions, literally these days, billions of individual transistors. That is, billions of these functions. The first computer contained about 20,000 of these tubes took up a whole room and generated an enormous amount of waste heat. The integrated circuits in your personal computer, in your smartphone, and so on, they have literally hundreds of millions to billions of transistors on a little chip. Here's an integrated circuit. This particular one probably has a few dozen transistors in it. Here's a much bigger integrated circuit with probably thousands of transistors. Here's a memory module from a computer, which consists of a whole bunch of integrated circuits, each of which probably has on the order of a few million transistors. And here, this is already obsolete, is an Intel Pentium 3 chip used in an earlier generation of personal computers, and again, probably has several hundred million transistors. So we've gone from this device, which allows one circuit to control another, to integrated circuits that contain hundreds of millions to nowadays billions of transistors which function similarly to this device. So what's happened in electronics is not so much a change in function over all these years, but a miniaturization and a huge increase in power because we are able to cram more and more of these control devices on a single circuit. And I just want to illustrate that with one example of that evolution. Here's a rather archaic device. We don't actually think about these devices so much because they're built into all kinds of things, radios. Here's a radio from probably about the 1950s. It's just an old AM radio. I'm going to turn it around and show you what's inside it. And inside it, you can see several tubes in their glass envelopes. There's a special tube that's got metal around it to shield it from electronic noise, but that is the insides of that radio. And the company that manufactured this radio would boast about how many tubes there were in the radio. Next to the radio, the tube radio from perhaps the 1950s, is a transistor radio, an early transistor radio circa about 1970. It's obviously a lot smaller. It can be powered easily by batteries or by being plugged into the wall. More on that in future lectures. And if I turn it around, you can see it's crammed with components, a whole lot of different components that we'll learn about, but in there are 9 transistors. And the company that built this radio boasts about this radio has 9 transistors, carrying on the tradition of how many tubes did it have. Well, my next radio I can't even take apart. If I did, you wouldn't see much in it, but a lot of black rectangles that are the integrated circuits that make it up, many of which are so complex they perform almost all the functions of a radio in one chip. So there it is, and it probably has in it, I'm guessing, I don't know what the circuits are in it, but I'm guessing probably thousands to millions of transistors, even in something like that, probably more like thousands in that on its integrated circuits. So there's the evolution of the radio: tubes, individual discrete transistors, and finally integrated circuits. Now, what's powered this revolution in electronics? Again, a revolution in the power of the electronic devices and the number of components we can cram into them, but not a revolution in the basic functions of these devices. So part of what's powered it is an idea that was promulgated by Gordon Moore, who was a co-founder of the Intel company that we all know about that makes the processor chips in our personal computers. And in 1965, he made a prediction. He said, as we learn to make integrated circuits more and more compact, the number of transistors on a single chip, that is a single piece of silicon that makes up one of these complete integrated circuits, would double every 18 months. And he was off by a little bit. Actually, the number of transistors has been doubling about every 2 years. And the graph here shows you that extrapolation up to where it's actual data up until 2015, and then it's an extrapolation beyond that to where we're headed. So we now have, in today's integrated circuits, today's computer chips and so on, we have literally billions of transistors, and that number is doubling every couple of years. That's the reason almost any electronic device you buy is obsolete almost as soon as you buy it, and you envy the people who have the newer one just 6 months later. So that's Moore's law, and Moore's law seems to be holding and will probably continue to hold for probably at least another 10 years, and then some fundamental limitations imposed by quantum mechanics may come in and make us have to rethink how we make very small miniature devices. Okay, so that's a quick history of electronics. Let me say a little bit now about this course, and then I'll move on and give you a little bit of a background on electricity. First of all, I'm not going into depth here in detailed physics. I'm not going to explain much of the physics of how these devices work. You can see other great courses for that, including ones that I've done. I'm giving you instead a kind of intuitive feel for electronic devices. I'd like you to be able to build basic, simple circuits. More on that in Lecture 3, how you'll build them. You will not come out of this course an electrical engineer, but you will have a sense of how the devices you use work. And let me also say a little bit about myself as your teacher here. I've been teaching electronics, as I mentioned, for about 30 years. I teach a course called Electronics for Scientists at Middlebury College, and it's not just for physics majors, it's for pre-meds, chemists, others who are going to use electronic instrumentation in their careers. We've had a course called Electronics for the Intimidated, for the non-scientist. And although I'm a theoretical astrophysicist by research, I actually love electronics. I've been an electronics hobbyist since I was 12 years old, and I was actually hired at Middlebury College because somebody left in the middle of the year who was teaching their electronics course, and I was hired. So that's how I got my job, by being an electronics hobbyist, actually. So let's talk a little bit about the basic things we need to know about electricity to understand electronics. So there is a fundamental property of matter called electric charge. And it comes in two kinds, called positive and negative. They don't mean the presence and absence of something. They're just names that Ben Franklin gave them. We know that like charges repel each other. So the diagram shows two positive charges repelling each other and two negative charges repelling each other, and that opposites attract. So we see also a negative charge and a positive charge attracting each other. And the protons that are in the atomic nuclei are our main carriers of positive charge, although there's something called holes in semiconductors that we'll see a little bit later that are really important in the way transistors and other semiconductor devices work. And then the electrons carry negative charge, and there are vast numbers of electrons, free electrons, in metals. So we can talk about free electrons as a way of distinguishing two kinds of materials. An electrical conductor is a material containing free electrons. And an example is the electrons in metals. Another example is the electron and these positive mysterious holes, which I'll talk about later, in semiconductors. But the point is, there are charges that are free to move, and that's what makes the material a conductor. And so the diagram at the top shows a bunch of positive charges. These are the cores of the atoms, and in a metal, typically, one or two electrons at the outermost periphery of the atom. When the atoms come together to form a solid piece of metal, they become free. They aren't bound to individual atoms. They're bound to the entire metal, but they're free to move throughout it, and that's what makes this thing a conductor. In an insulator, on the other hand, shown in the diagram at the bottom, the individual electrons, all of them, are bound tightly to the atoms, and they can't be removed. So that's a very quick description of the difference between conductors and insulators. There's a much more detailed description in terms of quantum physics, but I'm simply not going to go into that. So we have electrical conductors, and what can happen in electrical conductors is those charges can move. And I would like to introduce two quantities now, two electrical quantities, important quantities that we'll deal with throughout this course that speak to the movement of electric charge through conductors. And so we have two things. We have electric current. Current is a flow of charge. You sit and look at a wire and you count the amount of charge that goes down the wire in a given time. And the amount of charge that goes by in a given time is a measure of the electric current. It's like watching a river and saying, how many gallons per minute are flowing by? How much charge per, usually, second is flowing by in this circuit? The unit of electric current is the ampere. I'm not going to go into the detailed definition of the ampere, but an ampere consists of about 6 times 10 to the 18. Wow, that is lots and lots and lots of charges, of elementary charges, the charges on the electron or on the proton. The charges are the same, but they have opposite sign, going past a given point every second. An ampere is a fairly familiar level of current. If you have an old-fashioned 100-watt incandescent light bulb, the kind of thing that's going obsolete pretty rapidly, as we'll see in a moment, and why that is, that's about an ampere, a little bit less. In electronics, we'll be dealing mostly with milliamps, thousandths of amps, abbreviated lowercase m for thousandth and capital A for ampere. It's capital, by the way, because it's named after the Frenchman Ampere, who worked a lot with electric current and its relation to magnetism. So we're going to be dealing often with milliamps or MA in this course, and so I'll often use the term milliamp or label a current in MA. And here's an important point about electric current. The direction of the current is that in which positive charges flow. So if you have electrons moving through a wire from left to right, the current is actually flowing from right to left, and that's a little bit confusing, and you have to scratch your head about that. And you can blame Ben Franklin, who assigned those terms, not realizing that the dominant charge carriers in wires, in metal wires, are electrons. Then we have the voltage, the push that drives the current through a wire or through any other electronic device. And if you have taken any kind of physics course, you've probably learned that voltage is a measure of the energy per charge. The unit is the volt. If you want to know what a volt is, it's a joule of energy, the SI unit of energy per coulomb, the unit of electric charge, but we don't need to go into that. So, for example, common batteries, if you have a AAA battery or a AA battery or a C battery or a D battery, those are all 1.5 volt batteries. That tells you how much push they have. It tells you how much energy they give each amount of charge. A car battery is about 12 volts. The wall outlet in North America supplies typically 120 volts. In the electronic circuits we're going to be developing in this course, typical voltages are in the range of 5 to 15 volts, sometimes a little lower in some really new circuits, and sometimes a little higher maybe in a power amplifier. So we have a flow of charge, current, and we have a push, the voltage that pushes current through devices. Okay, so now let's develop a couple of relationships that will help us to understand how current and voltage behave in circuits and how they're related. So I'm going to move over to our big monitor, which we'll be using in this course as a kind of electronic blackboard. And if I ever have to do mathematics, and this is not a heavily mathematical course, but there will be a little bit of math in it occasionally, I will do that on the big screen. We'll also use the big screen to display the output of certain instruments so we can see them a little more carefully. So let's go and look at the quantity which we're going to call electric power, a third quantity in addition to current and voltage. So electric current is the charge, the amount of electric charge flowing per a given time. Voltage, as I indicated, is the energy each charge has or gets from the energy source in whatever circuit it's in. And so if I take and multiply these two together, current times voltage is going to be charge per time, that's current, energy per charge, that's voltage. Little algebra here, you notice charge on the top and charge on the bottom. I can cancel them, and I end up with energy per time. Now, if you've had a physics course, energy per time, you know, is power. Power is the rate at which a system delivers energy, consumes energy, loses energy, produces energy, transfers energy from one form to another, whatever. It's a rate. It's the rate of energy consumption, generation, whatever. And in electric circuits, this little sort of word equation tells us that current times voltage gives us power. And power has the units of watts, named after James Watt. You may think of watts and kilowatt hours and things like that as uniquely electrical. They aren't. Watts measures energy rates in any kind of system. But in electricity, watts are particularly convenient because multiplying the current in amperes times the voltage in volts gives you the power in watts. Okay, let's do just a quick example where we worry about electric power. Power being watts, amps, times volts. So we'll do some power examples, and we'll remember that power in watts is simply current times voltage. Later we'll use symbols for these, but right now I'm just going to call it amps times volts. So here's a question. Your car's 12-volt battery delivers 125 amps while it's cranking the starter motor, trying to get the car started. What's the power it supplies? Well, power is amps times volts. And here we have 125 amps times 12 volts. That's going to be a little bit more than 10 times 125. It's going to be somewhat over 1,000. Comes out 1,500 watts, or 1.5 kilowatts, where K means 1,000. That's, by the way, roughly the same power that a stove burner consumes. So if you have a hot stove burner on high, it's consuming power at the rate of about 1,500 watts. And that's the rate at which your car's starter motor is extracting energy from your car's battery when it's cranking, when you're just running the headlights or running the GPS or running the instrument panel or the ignition system, it's less. But while you're starting, the battery's got to be able to supply a lot of power, over a kilowatt. Here's another example, perhaps one you worry about more in these days. Your cell phone has typically a 3.7 volt battery. It consumes about half a watt while you're talking. Significant for that tiny little device. And about 25 milliwatts, thousandths of a watt, when it's on standby. What's the current delivered by the battery in each case? Well, we can handle that one with some algebra. We can rearrange that equation, dividing both sides by volts, and we have amps is power divided by volts. So when we're talking, we've got half a watt, 0.5 watts, divided by 3.7 volts, and that comes out 0.135 amps or 135 milliamps. Again, that's a significant amount of current for a relatively small battery to deliver. When we're on standby, it's 25 milliwatts over 3.7 volts, and notice the milli in milliwatts makes the answer just come out in milliamps. I don't need to do a conversion. We'll often be doing little tricks like that. So in standby mode, you only consume current, charge flowing out of the battery, at a much lower rate, and we could calculate by multiplying these currents by the voltage what the actual power is in that case. So there are a couple of examples of power as volts times amps. Okay, let's now look at one other relationship between current and voltage. And it has to do with this pushing by voltage of current through a conductor. And conductors, typically, with the exception of things called superconductors, which we won't go into in this course, have resistance. They don't let current flow easily. And the resistance of a particular component is a function of both the material it's made of and its geometrical size and shape. And there is a simple relationship between current and voltage when we know the resistance of a material, and it's called Ohm's law, and it says current is voltage divided by resistance. I is going to be our symbol for current, V for voltage, R for resistance, so we can write it I equals V over R, or we can manipulate it algebraically to write V equals IR, or R equals V over I. Those aren't different laws. They're just different ways of writing the same thing. The unit of resistance is called the ohm, and if you have 1 volt and it pushes 1 amp through a material, a conductor, then that conductor has a resistance of 1 ohm. By the way, Ohm's law is not a deep fundamental law like the laws of electromagnetism, Gauss's law and Faraday's law, Maxwell's equations, and so on. It's not like the second law of thermodynamics. It's not something fundamental. It's something that happens to be true, at least approximately, for a number of materials. So resistance measures the resistance to the flow of electric current, and it's measured in ohms. And we're going to just use Ohm's law to do some examples, but before that, let me just show you some resistors. So I have over here some devices that are made to have electrical resistance. They typically look like a little tiny cylinder with some stripes on them. They are designed to have particular resistances. They're typically made of carbon that's been compressed. Here's a slightly bigger one. Here is a variable resistor that might be a volume control in an old radio like this one. Here's a big, heavy resistor that can dissipate a lot of power. And here's an enormous variable resistor that I'll use later in the course. And here is a big resistor. The hot plate burner is simply a material that's got a lot of resistance, or not a lot, but enough resistance that current flows and heats this device up. So those are resistors. Over here I have an ohm meter, which I'm going to use to measure resistance. In subsequent lecture, we'll come to understand how this device works. I'm going to grab this resistor, which happens to be a slightly bigger one than the little one I showed you, but that's because it can dissipate more power. I can read the color code off it. I'm not going to teach you about that, but that says this is a 2700 ohm resistor, and it says 2.64 kiloohms. There's a little gold band at the end of this resistor that says it's good to within 5%, and that is within 5% of 2.7 kiloohms, or 2700 ohms. So there is a resistor, and I've just measured its resistance. So many kinds of resistors. Well, let's take a look briefly at how we might use Ohm's law to do some experiments here. So let's talk about using Ohm's law just briefly. Again, Ohm's law written in 3 different forms, but they're all equivalent. And so here's the question. A typical 120 volt household outlet can supply up to 20 amps. After that, the circuit breaker goes to keep so much current from flowing that wires would heat up and maybe risk a fire. What's the minimum resistance you can connect across it? And what's the maximum power? Well, let's use the form resistance equals volts over amps. 120 volts over 20 amps, 6 ohms. You can connect 6 ohms, 7 ohms, 8 ohms, 100 ohms, a million ohms, no problem. You connect 5 ohms, you're going to blow the circuit breaker. Power is I times V. That's 20 amps times 120 volts. That's 2400 watts, or 2.4 kilowatts. more than that car starter, but not much more. More than that electric stove burner, but not much more. An electric stove burner would typically be operated off a bigger circuit. And here's another one. What's the voltage across a 1.8 kilo-ohm resistor when it carries a current of 5 milliamps? Well, voltage. So I'm going to use the form V equals IR. V equals IR, 5 milliamps times 1.8 kilo-ohms is 9 volts. Little 9-volt battery, the kind with the little snaps at the top. You put a 1.8 thousand ohm, 1.8 kilo-ohm resistor across it, 1800 ohms, and you'd get 5 milliamps flowing. So there's how we use Ohm's law. And notice something. When we have M in milliamps, which we're going to use a lot in electronics, and we have K in kilo-ohms, which we're also going to use a lot, those two cancel. The thousandths and the thousand cancel, and we get the voltage right out in volts. Okay, well, let me wrap up by just showing you a few interestingly special resistors. Inside your computer's hard drive, if you still have a computer with an old-fashioned mechanical hard drive, is a resistance that depends on how much magnetic field it's exposed to. And as the hard disk spins and the magnetized information goes by that, its resistance changes, and that's how you read the information. Here's another interesting resistor. This is a photoresistor. Its resistance changes with light, and we're going to use photoresistors and related devices in several circuits we'll be building later. So I'm connecting the photoresistor up, and you'll notice it has 0.123 kilo-ohms, 123 ohms. And now I simply cover it up with my hand so it can't see the light, and that number goes up. It's already up to about 50-something thousand ohms. So this is a light-sensitive resistor, a photoresistor. And again, we'll use that in a lot of useful applications. I imagine you can even think of some right now that you might want to use. Okay, so let's wrap this lecture up. First of all, we've seen the essence of electronics. It's about one circuit controlling another. We have electric current, the flow of electric charge. We have that occurring in conductors. Its unit is the ampere. We have voltage, the push that drives the current through a conductor. It's the energy per charge. Its unit is the volt. We have resistance. Resistance R resists the flow of current, and the unit is the ohm. And electric power is voltage times current. And finally, we've worked with Ohm's law and understood how voltage and current are related and related to resistance. Well, that's all I have to say now, except I want to remind you that each lecture in this course has with it a project, which you are welcome to do. It's separate, but you can do the project, and the project is sometimes a simple calculation, but more frequently it's going to be you're designing or working with a circuit. So here's the project. If you'd like to go on and do the project part of this lecture, you're welcome to, but you certainly don't have to. The first is about a real situation in which your car battery gets corroded, there's a little too much resistance, and you can't start your car. And the second one is about an LED lamp, and that will show you why an LED lamp is so much more energy efficient than that old-fashioned 100-watt incandescent lamp. So Lecture 1's project is about hard starting of your car and LED lamps, two very practical applications of the simple concepts you learned in Lecture 1. So the first question is about your car. The connection between your car's battery and the wire supplying the starter motor has corroded to the point where its resistance is 0.05 ohms. That doesn't sound like much. If you ever looked under the hood of your car, you've seen a big hefty wire that's clamped around the lead terminal of your battery, and it's a common problem for that to corrode and its resistance to increase. So here we've got one where the resistance has increased to 0.05 ohms. When you try to start the car, the starter motor draws 100 amps. That's pretty typical for a starter motor. And the question is, what's the voltage across the bad connection? Your second question is, an LED lamp operates at 120 volts and puts out the same amount of light as a standard 100-watt incandescent lamp. It draws 150 milliamps of current. Compare the power consumption of the two lamps. So take your time, work your problem, and I will come back with the solutions. So here are the solutions. Here we have the car to begin with. Well, this is a straightforward application of Ohm's law. We know the current and we know the resistance. The current is 100 amps. The resistance is 0.05 ohms. Multiply those two together and you get 5 volts. Now, a car battery is a 12-volt battery, so that leaves only 7 volts across the starter. Not enough to start your car. That's why you're going to hear, vroom, 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 and you're not going to get anywhere that day. So there's one example of Ohm's law applied to a simple situation involving a resistance and a current. So we have our LED now, operating 120 volts, same amount of light as a standard 100-watt incandescent. Is 150 milliamps, or 0.15 amps. We multiply that by the 120-volt voltage, and we get 18 watts. And that's only 18% of the incandescent lamp's energy consumption rate. And you can see from that why it is that incandescent lamps are rapidly becoming obsolete in an age when we worry about energy efficiency.